So Dan has been like a kind of a, let me put it like that. I'll give you Dan, like kind of becoming a legend, let me tell you, like that in the field. So he's an associate vice president of the research at the University of Texas at Austin and executive director of TACC, the nationally recognized leader in the high performance computing. It has been involved in supercomputing for more than 30 years. The PI of a number of National Science Foundation projects, building all these supercomputers over the years. And from the Rapid side, we've been working with TACC almost now, what, 15, 16 years on series of systems. But this is the very latest system called Horizon, and that's what he will be talking today. So let's give a big welcome to Dan.
Thanks very much. And just the one mic, or do I have to talk? All right, great. Well, thanks, DK. It's good to be back here. I point out it's only 7:40 a.m. Central Time, and I usually don't have to be nice to people before 8 a.m., so I'll do my best here, but it's awfully early. I guess it's earlier for Yifeng, and he has to go next. I think this is I've lost track of how many times I've come to this meeting, but at least 7 or 8, as DK said. We've been working together on various tax systems since Ranger in 2008. So going way back now, and one of my themes is the rewards of long-term effort. And yeah, I want to talk a little bit about what's coming down the pipe in resources and talk more about sort of what the implications of that are. You know, the two big ones being the new NSF Leadership Facility Award, which is going to be a long journey. It's been a long journey, but that just officially started a few weeks ago. The National AI Research Resource and Connect It, but mostly I want to talk about 2 or 3, you know, sort of long-term, we could say opportunities, but we'll say challenges that we face that I think we can get some help with from the community in the room here and other places. I'm also going to cop to the fact that this is a very close repeat of the talk I gave at the TIES workshop at PERC just a couple of weeks ago. That was on the Monday morning at 8 o'clock at PERC, and with the CrowdStrike event the Friday before. Almost no one actually made it to the talk, including me. I did it remotely, so DK was stuck in Detroit at the time. So given that, you know, maybe 9 people saw it, I felt like I could whip it out one more time here. So and see what goes on. So, but anyway, I want to talk a little bit about TACC, a little bit about the Leadership Facility Award, and then lead into 2 or 3 challenges that I want to go a little deeper on. So almost all of you, I think, at this point know who we are. We're big MVAPIC users. We run a whole bunch of machines, mostly for the NSF community, except Lone Star, which is our Texas machine there, immersion cooled. Talk more about cooling a bit too. But we have, you know, maybe 20,000 servers, but 1 million CPU cores, 1,000 GPUs, and that's all growing pretty quickly. Actually, now we have a fair number over that in GPUs. We use about 6 megawatts of power, and we're going up to about 25 megawatts of total capacity in the near future. And they're all full all the time. Since I last spoke to you last year, we've added 2 new machines, Vista and Stampede 3, and these sort of, well, they really do different things. Vista is our first all NVIDIA-based platform. It's actually very similar to the machine that was discussed in the keynote yesterday morning, in that it is both Grace Hopper chips from NVIDIA, but also the Grace nodes. So even our pure CPU nodes are all ARM-based. And so I'm going to show you some ARM benchmarks later on in the talk as to why we think that's a good idea. But it's really the first one we've done with no x86 in a very long time. And it is currently an early user. It'll go into production soon. Stampede 3 is not surprisingly a continuation of the project Stampede 2, which is one of our sort of NSF capacity platform. And it's continues as Stampede 1 and Stampede 2 were, which together ran, I think, 21 million jobs for users over their lifespan. It's now an all Intel system, although inevitably it's going to end up with some H100s in it because GPUs are finding their way into everything now. but it's still primarily an Intel-based system that went into production in May. And I'll show you a few benchmarks from that too, but just one or two. But so at this point we have, and I'm going to actually tell you what's under the embargo things, but a number of different systems with both expanding GPUs and CPUs. We have historically been more of a CPU-oriented organization, right? And Frontera was a $60 million box back in 2019. In 2019, we said the words AI much less frequently than we do now. So we put, 60 million, I put about 58 million into the CPUs, right? With 470,000 total cores. It's been an upgrade since we got those numbers, DK, on your slides. I don't think we ran the MPI benchmark above 448,000 cores, but with just a little bit of a GPU subsystem added on, 90 quad GPU nodes. But the balance has changed as time has gone on, right? With now, so again, Frontera was sort of frozen in time in 2019, so it's Cascade Lakes with Volta class GPUs. Lone Star 6 was our 2021 machine. It's all AMD EPYC processors, colloquially the Milan processors, where just 600-700 nodes, sort of a mid-scale one for us, but it keeps us current on what's going on with AMD. And then we added a bunch of A100s in there for more of the AI and MD users. So it had 255 A100s. It has a few H100s on it now. Stampede 3, I mentioned, is actually recycling some of the components from Stampede 2 because really at this point, after 5 or 6 years, with what's sort of happened with technology, the end of Dennard scaling, Moore's law more or less continues, but not in the way that people want it to. In terms of higher performance, the servers last longer, right? So we did buy 600 new Sapphire Rapids HBM nodes in that machine, but we still have the Ice Lake and even some of the Skylake nodes just as a throughput queue in that. And because the charge rates are cheap, we actually have the longest wait time on the 2017 era Skylake nodes, and slightly shorter on the Ice Lake and shorter than that on the Sapphire Rapids because users don't want to change their scripts and everything just works. But altogether, it has a couple of thousand compute nodes, about 150,000 cores. It has a little bit of the Intel Ponte Vecchio GPUs, mostly as a pathfinding experimental system. When those came out, they were primarily in Aurora at Argonne, a nice 65,000 GPU machine that almost no one has access to, relatively speaking. So it's not the best platform for getting lots of people to port their codes over, unless you're in the DOE complex. So we just have 20 quad GPU nodes on there that let's just say I didn't spend a whole lot of money on. To sort of explore the Intel GPU SYCL One API side of the house, because of various NAIR things, we'll end up adding some H100s to that machine. So Vista is the newest one. As I mentioned, it's all ARM with the Grace processor. For all the CPUs, it's actually 860 nodes. I don't know why I put 840 on there. It has 600 H100s in it. So it's sort of our looking towards more and more AI workloads machine. But we still have a few hundred dedicated CPU nodes because that's something we're not going to let go in any future machines, and that will take us to Horizon. And again, officially we haven't ordered yet, so officially I shouldn't say what's in it, but I will say right now, if we had to issue a purchase order today, and things are subject to change, right? NVIDIA is the leader in the clubhouse on this, and it will also be an ARM-based system, and therefore also an InfiniBand system with it coming from NVIDIA. The CPU nodes, the pure CPU nodes, will be the next generation, past Grace, of Vera, which will be the NVIDIA's second generation ARM chip. The GPUs will be Blackwells, not surprisingly, the ones coming out next year, because we're going to deploy those racks probably a little more than a year out, 14 or 15 months from now, looking at an October, November deployment on that of 2025. But the commitment I made will probably come up just a little bit short on this with pricing changes, but we're going to keep a substantial CPU footprint because, you know, AI workloads are everywhere. We have tons of them. We have lots of non-AI stuff that runs on GPUs, but 60% of our user applications that we see in our user base still don't. They're CPU based. So we're going to keep order 1 million cores of CPU in the machine to support our long-running existing users and codes that don't move over. But we'll also have order 4,000 GPUs in that machine. So, you know, sort of a big leap up from where we are now on the GPU side. That would give you, again, for unannounced parts, it's always fun, but for rough peak performance would be around 400 petaflops at double precision. For our sort of traditional scientific users, if you want to measure in, say, bfloat 16 or some of the AI units, it's 10 exaflops plus, because there's this huge nonlinearity between what you get at 64-bit performance and what you get at lower precisions now, which is one thing I want to talk about. So again, for the new system there, Horizon, with several hundred petabytes of flash storage and various other things, it's going to come in probably just under 10 megawatts, right about what our center is now. You know, at right around 9.5 or 10 megawatts, but it's still going to be a fairly substantive footprint, although better than we could have gotten with some other technologies that I'll talk about. So one thing we're seeing in the recycling of nodes in Stampede 3 is a part of this, but this is a theme, and one that I think even on DK's talk yesterday, you saw how many forks of MVAPIC they're supporting for how many different kinds of processors out there. So the leadership facility is, you know, several $100 million investment from NSF, right? The FAST and NAIR and the various AI facilities that are proposed are, you know, anywhere from 2 to 12 billion. Not that those numbers will ever actually pass Congress, but but multi-billion-dollar infrastructures. And so I think one theme we're going to have to deal with is the, you know, infrastructure is getting larger, right? Even the big cloud systems, when you sort of break them down, Microsoft, for instance, is deploying huge InfiniBand connected clusters that they're going to keep in service for more than the 4 years we used to around scientific computing, right? I think just funding cycles have made us keep it, but things are starting to last 6, 7 years, which means we're going to have a lot more heterogeneity and a lot more stuff in the field, which means software and data is going to keep getting harder and harder. So with that as a little bit of context, let me just dive into the LCCF for just a few minutes. And I'm not going to go too deep on details because, again, I want to get more into issues. But yes, if you haven't heard about this, and you probably have because I've been talking about it forever for things that will come in the next couple slides, but NSF has launched the new leadership facility. It was officially funded after many, many years that I'll talk about on July 11th. So just about a month ago. So it will be primarily hosted at TACC, although it's a distributed facility around the country, and it's a huge and sort of different investment and a long-term investment in computing infrastructure, which is important for NSF. And once again, I'd like to say that the MVAPIC team remains a key partner in all of this, Ohio State. In fact, you should have gotten a new sub-award on Monday, DK, for this. At least your sponsor projects office did. But OSU is a funded partner in this, and specifically the MVAPIC team. And part of it is we insist on any machine that we put up, we have at least 2 MPI stacks, at least one of which is open source on there. Mostly so we know who to blame when it comes to interconnects. And by the way, we still have a variety of interconnects. Stampede 3 is on OmniPath with Cornelis. But again, Horizon's going to be InfiniBand, the 800 gig version of it. But now, for all of our x86-based systems, for years we've supported Intel MPI with MVAPIC, and usually MVAPIC has been the top performer, with some leaps back and forth as the competition continues through the years. Now on the ARM side, NVIDIA supports OpenMPI, but we're still putting an MVAPIC build on there too. So we have OpenMPI and MVAPIC in a bake-off, and having a good network stack is a key to our success. I'll talk a little bit more about why later. But let me just do a little background on the leadership facility. So by the way, it's a long road, and particularly for those of you who are students, one thing we've noticed with the younger workforce is getting them involved in projects where the outcomes are years away. It's hard to do, and patience. but sometimes having a long view is useful. DK started on MVAPITch, what, 23 years ago? At this point, it's been a long road, even though you see the year-to-year milestones are short, the whole project is long. This is something that we've worked on for, I like to say ever, because I'm trying to get NSF to do this for more years than I can count, but the original solicitation that led to the LCCF being funded came out in 2017, right? So it's been 7 years and 3 months to get this thing to come to life. And there was pretty much work on it every week for those 7 years and 3 months to get it due. So May 10th, 2017 was when the solicitation came out. We put in the proposal the November 20th of 2017. And yes, if you're on the calendar, that would be the Monday after supercomputing, because that's the worst day to have large proposals due, and the Monday of the week of Thanksgiving. So that's when large proposals are always due, is on the worst possible day. So to put it in a machine for a large supercomputer. But it asked really for two things, right? Deploy an HPC system, the phase 1 system, that became Frontera, right? And it was to have two purposes. One was to deal with the workloads we had now, or now in 2019. And then to look at the feasibility of a longer term LCCF type platform. And so that's more or less what happened. So, and then again, it took till July 10th. Technically, the start date is July 1st, but they didn't actually put it in the awards database till July 10th or tell us until July 11th that it started on July 1st. So after 7 years and 2 months of planning, where we got audited 4 times to get the budget down to a dime for every dollar of expenditure, we were 11 days late on the day it started, and so we'll never be within $1 million of that plan. 4,000 pages of planning submitted 3 different times, and they broke it before it started. But anyway, so I could tell you about many of the really stupid arguments along the way, and how few of them had anything to do with science. But I think the important thing here about the NSF leadership class facility, obviously it's a big machine. Again, Frontera was 60 million. The various Stampede systems were 30 million. So really large investments, but not at the level of like DOE's investing at. And it's been since 2011 that NSF really invested in a big machine. And so this one, the hardware budget is more like 175 million. So it's substantially bigger than where Frontera was. Plus we have to build a place to put it that they're actually paying for a change. The big change here for NSF, right? There's the scale of funding, and that's great. Obviously, I think it's awesome because I get to build big toys. But to me, the biggest change is how they're funding it, right? Which is from the major facilities account. So this is what funds all the other NSF large facilities, the Vera Rubin Telescope, LIGO, the Large Hadron Collider, NEON, the Ocean Observatory, all of these sort of big, long-term, multi-decade scale science instruments, right, that get, usually it's NSF and DOE and often foreign partners on some of these, but things that spend billions of dollars and win Nobel Prizes. And we've never invested in computing in the same kind of way and in the computing infrastructure, which means, you're running NEON, the National Ecological Observatory Network, right? You spend $500 million building towers, platforms, planes to put together ecological data, and you want to build a database over a 20-year time scale and then make it available to researchers to analyze. You have a huge amount of data processing and computing. If you go to the NSF computing providers, they're like, hey, I got funded to do this system. All the centers have complained about this forever. It has a 4-year lifespan and then it goes away, right? And maybe we'll win another one. That is not a good risk management plan on a $1 billion project for your computing, so they all end up building their own infrastructure that sort of kind of works and underinvests in computing, and it's a mess, right? So this is putting the investments on the computing and data and AI side of the house on the same footing as the investments in telescopes and ships and large instruments, right, that run for a long period of time and have long-term stewardship of data, right? And yes, Horizon will get old at the same speed as the other machines, but there's a potential refresh. The committed life of LCCF will get rebid in there somewhere, so it won't necessarily all be with us. So the construction phase just started, so we'll hit production sometime in late 2026. full production, transition to operations. Users will have been on the machine for months at that point. But the plan is that'll operate through 2037 with another 10-year renewal through 2047, right? So NSF's committing to have an infrastructure in place for 23 years, right? Had a call actually day before yesterday with like the next generation very large array, replacing the big telescope in New Mexico with one that will be like 1,000 miles wide with antennas every 50 miles or something. And they're in their own design process, they're looking at starting it in 2028, full production in 2032, 10-year run, right? By the time they have their finished data sets processed, they need a commitment through 2042, right? And that's just something we've never been able to do before. So yes, it's the next big machine, but it also signals that they're going to take this infrastructure seriously in some ways for the first time as a long-term permanent thing. And that is a really big change for science that's, almost more important than scaling up the dollars, although I'm very happy to have the dollars. So there's really four main components of what's going into the facility. One is a new home for it. I didn't bring the pictures, but we're building 15 megawatts of new data center with an option to add 5 more should we need it down the line. But the initial build out's 15 megawatts. There'll be a new visitor center and all that kind of stuff that's attached to TACC. We're actually not building this onto the main TACC data center, which we'll keep and is already a 9.5 megawatt data center. And that will still be where Vista lives and things like that. But we're building it with a colo vendor. So we have, and this was sort of fortuitous timing, but there's so much data center being built for AI. It was reasonable to expect we could find one, but we found a data center that at the time we got funded in July is built out as a shell so that we can do, so the concrete's there, the substation's there, the building is complete. But now we can do all the customizations you'd want to do for liquid cooling, underfloor water. I have this on a slide somewhere, but our rack density for the GPU racks will be 216 kilowatts per cabinet. So you have, the air-cooled version of that is just, a small bomb. It absolutely has to be liquid cooled, right? So we can get the power density and the cooling technologies and the other stuff that doesn't go into commercial data centers because we're actually paying to change the build out of the data center to be, what we think of as an HPC data center instead of a, IT type data center. So that's one big component of the funding. The second one is, of course, the actual computing and storage systems. Horizon is the big machine, but we'll replace our long-term archive system, our data publication system. All of those will be a part of this. There'll be an interactive system. There's a fairly large investment in software and services around this. And of course, education and outreach is a big part of it. So, and again, it will physically be a distributed facility as well. The big chunk will be in Austin, well, technically Round Rock, about 7-8 miles from where TACC is now. For the new facility, but obviously Horizon will stay in Austin, right? Frontera and Vista keep being available, but there's going to be a small quantum test bed that's funded at NCSA, and they're also going to look at some of the I/O issues around the new accelerators at NCSA in Illinois. There's a high throughput system looking at sort of large-scale streaming inference off the other big instruments and high throughput data, the sort of open science gritty stuff that SDSC has long been involved in, the hand of Frank Werthwein there. But that's going to be deployed at SDSC. There's a storage and data curation system really focused more on data collections and publishing, where we'll also mirror the data in Austin that will come up at the Pittsburgh Supercomputing Center. And then we'll have an interactive system to support sort of accessibility, teaching, a lot of data science curriculum at the Atlanta University Consortium. It'll physically be at Morehouse College in Atlanta. And then we'll have people distributed across all these sites as well, plus here at Ohio State and at Cornell. And then we're supporting some of the actual applications to be ready to run on day one on the new system. We had 20 that we supported in the planning process. We're down selecting to 10, and those will be announced shortly of the apps that will keep going. At least one of those people's in the room from those teams. So, and so again, timelines, we're officially in construction That doesn't mean there's a lot of bulldozers moving around. It means we have construction money. Started July 1st. Couldn't actually spend $1 on this until July 1st, so, or July 11th. But at this point, the data center should be ready by a year from October with the internal build out on it. And so we'll get the Grace Blackwell racks first, perhaps as early as by supercomputing next year. But by the end of the year, certainly, end of the calendar year, we'll put users on sometime, hopefully around the end of the first quarter of 2026. And then that machine will be around until 2031 or 2032. And, assuming NSF and Congress can keep us funded, there'll be a replacement system in that time frame. So, again, though, 6 to 7 years on the floor is sort of what we're expecting for these machines instead of what used to be 4 or 5 years on the floor. So that's the story and sort of the investment. And by the way, when you start adding those things up, it's about $175 million for hardware, $150 million for civil infrastructure. There's a whole bunch of contingency around it. There's the storage, there's the software, the people, the education. It's order $400 million that's going into this. So it's a lot of money. At the same time, there's the attempt to build out what's known as NAIR, or the National AI Research Resource. And officially, they say they've launched it, but if you look carefully at all the sites, it always says NAIR pilot, and the difference between pilot and actual NAIR is one of those will require an act of Congress and funding, and the other one is what we're doing now, which is the unfunded sort of volunteerish effort to throw together an AI research resource out of existing budgets and existing machines for the most part. So, so the pilot infrastructure has no new money. There's only technically $30 million in this year's budget for it. But the ask is for $2.6 billion to build this out over a 6-year span. And, nothing's going to happen realistically with budgets till after the election, but at some point, probably in fiscal 26, this will become a reality. So, and be much bigger, but the odds of getting anything at that scale through Congress at the moment are fairly low at that one, but odds are Horizon will play a big role in this because it will have multiple thousands of GPUs, and I don't know where they're going to get enough money for multiple thousands more GPUs in that time frame, but ideally, once it's up and running, there'll be a stable stream of funding for it, and resources will run on 6-year cycles and get replaced sort of in 3 cohorts, so every 2 years, there'll be a batch of new machines and a batch of machines retiring. So, the sort of gist of that is we're going to have larger resources coming, right? And the DOE machines will be even bigger than the current ones if they get their way. So they're going to have longer individual hardware lives, right? So 7 years is not going to be an unreasonable lifespan for a machine. We know that we're going to have user demand that keeps driving the data sizes and the computation challenges through the roof. When I was flying up here Monday night, we actually had 200,000 core jobs going simultaneously on Frontera, and another one at 800 nodes and 2 at 500 plus nodes, right? So, which are bigger than, we had 5 jobs running that are bigger than most of the systems in Access, right? The NSF ecosystem. Just 5 single jobs running simultaneously that were bigger than, your average 500-600 node cluster can handle. And we see that all the time. Again, more than one running at 2,000 nodes. So we're going to have no shortage of challenges. But today, I just want to maybe dive in for the next 20 minutes or so on 3 things. One is, of course, interconnects and where that market's going and what it means for us, because MVAPitch is all about exploiting your interconnects. And one is about how we need to use AI hardware and sort of our general thing. And then the last one is a little bit on the climate and sustainability, because I know that got asked about yesterday. So, so this slide I actually threw up for the first time at this meeting last year. And so this is a slide, some benchmarking I found from Meta, where they don't actually tell you what their models do, but obviously one could expect this is picking which ads you get to see, because that's obviously the most important application of AI. But this is the time spent on their, all these companies, X, Meta, Microsoft, talking about how many 100,000 GPUs they're buying at roughly $30,000 a piece. So you do the math, and they're all spending multiple $billion on infrastructure for this. And then they spend a fair amount of that multi-billion-dollar infrastructure sitting around waiting for the network, which seems like a bad plan, right? And we've heard from the DeepSpeed team and from others about what we can do to make some of this better. But the network's getting thick in these machines too to sort of support this, right? If you look at the NVIDIA designs, if you look at most vendor designs, it's sort of a rail per GPU. We're going to do in Horizon, we'll have an 800 gigabit link for every dual Blackwell, because it's a single silicon module. So there's 2 Blackwell dies on there, but but each one will have its own 800 gig link. And some of them are even denser than that, right? If you looked at the NVIDIA roadmap yesterday, they have NVLink on one side and NVIDIA on the other, right? So still can't figure out how I'm supposed to invest in that much at the first level for nodes, because then it's 40% of your node cost. But for these kinds of apps, and from the benchmarks I see, both latency and bandwidth seem to matter, which is interesting because, for the first 15 years of cloud computing, it was, why do you crazy HPC people invest in high-speed networks when you obviously don't need them for enterprise workloads? And then AI came along and rewrote the script to the point where I think the last number I heard from Microsoft is they bought 29,000 miles of InfiniBand last year. That's in miles, which is not our normal unit for InfiniBand, right? But between Frontera and Stampede, we had 15,000 servers. We had maybe 200 miles of InfiniBand cable in the room. So something at several hundred times that scale, which is why InfiniBand is now expensive and hard to get, is they bought 29,000 miles. Remember, the max cable length is 100 meters. So you can sort of figure out they must have at least 1 million endpoints that they put up on InfiniBand, right? If you want to talk about a big fabric to have to do collectives over, think about 1 million endpoints. But it's because of this, right? They're spending, in fact, this year, hundreds of billions in AI infrastructure across the industry, and then they're seeing a third of the time waiting for network for that. So, which means, probably good things for the network market in the long term. In the short term, it's just making everything really expensive. So since I put that slide up last year, and a few other slides I had around this whole point of AI needs networking just as much as HPC does, or maybe more, I've been asking every vendor I talk to who is operating these AI systems, the cloud vendors, et cetera, when you're boosting AI efficiency, what matters more, bandwidth or latency? It's surprising the level to which no one can actually answer that question, despite $300 billion of investment in it this year. You think you'd figure out the answer, then spend the $300 billion, but not everybody's a scientist. But it certainly seems like a question worth answering. As the last couple months, I've been starting to hear more and more that bandwidth is perhaps a little more important than latency, but they clearly need both. And they don't really know. But the conventional wisdom seems to be system-wide, you need a ton of bandwidth. But it's sort of locally even more. So those NVLink, DGX architectures, right, is to have sort of what we'd call the top of rack switch level, way beyond 400 or 800 gig per GPU, right? Ridiculous amounts of bandwidth. But I'm not sure anybody's really validated that assumption at large scale. But again, you'd think before we make more 9 figures investments in systems, we'd like to know more about that. But one of the great things about this sort of AI surge at the moment is it is forcing us to have better HPC networks and more options for them over time, whether it's low latency RDMA-based Ethernet, whether it's InfiniBand or OPA, or the Rockport stuff or whatever comes along. There seems to be a lot more investment in these things. And that sort of leads me to the next thing I want to talk about, which is if you look at the markets going forward, for all future systems we need to build, Horizon and then some, there's a lot of investment in interconnect. Hopefully it'll still be exactly the one we need for HPC, but if they decide bandwidth matters more than latency, it may not be ideal. But we're seeing the same things with processors and file systems, right? So in fact, the forecast I'd read for the AI market was $300 billion a year in hardware and data center. I recently saw a number that said over, this year, next year, it may be more like $1 trillion, so 500 billion a year, than 300 billion a year. But, some measurable fraction of the world's GDP is going into this, right? And HPC still is a $10 billion a year market. And that's the math that vendors can do, right? Is that you're selling at least 30 times as much gear into the AI market as you're selling into the HPC market, right? And if that's true, we pretty much know where the hardware is going to go, right? Everything that comes out is going to be AI optimized, and HPC will be an afterthought at best in scientific computing in that. And you already see it in the fact that look at pretty much anyone's roadmap, particularly like the GPU roadmaps, and 64-bit, if you look to the next generations from the current ones, there's really no improvement in 64-bit performance, right? So for those of us doing a lot of 64-bit stuff, you're going to be flat unless we get creative in how to do it, right? Because the next gen GPUs will cost a lot more, but be roughly the same speed. But they'll be very highly optimized as you go down in precision. And then again, the same thing's happening in file systems and just in everything, right? So what we're going to have to do is adapt to that marketplace, right? Where we know the investments in AI, but we still need to do scientific computing. And I would argue the vendors will be hopeless on helping with this, right? The national labs will go kicking and screaming last because they can spend enough money to stave off the markets for a while. But it's in academia where we're going to solve this problem, because it's in academia where we solved this problem last time. And last time for me at large scale was really in the early 1990s. Which when I was just getting into this, that was a cluster we built at Clemson. That was the second Beowulf cluster. It was called Brendel way back when. Our goal for that machine, and I remember, laminating the shelves for that in my boss's garage in the early 90s. It was really enterprise scale stuff. And our goal was to do a $50,000 for 1 gigaflop. I did mention we're doing a 400 petaflop machine, right? So how many billion factors? We're what, 10 to the 12th larger now. But what was happening at that stage is it was 1991, 1992, the Cold War was ending, and all of the sort of custom silicon supercomputing vendors who at the time, Seymour Cray's company was building gallium arsenide circuits because silicon wasn't going to perform at a high enough clock rate. But everybody was custom silicon, custom chips was the only way to do supercomputing, right? Very long vectors, right? And almost all of those companies died doing that, right? There were about 30 in that. Most of them didn't survive or got smaller. They've since all been acquired. Cray, SGI, some of those other parts, all owned by HP now, disappeared along with Compaq and DEC. But most couldn't sort of adapt to the changing market conditions. But for the rest of us, particularly those of us without huge budgets, but led by my friend Thomas Sterling and Don Becker, they started the Beowulf project depending on which history book you read. It was really 93, but they say 94. But 30 years ago, and what Thomas said at the time, and I wasn't in the first meeting, but my advisor was, he reported out, so about that is what we needed to do in scientific computing was to be bottom-feeding scum suckers. And this is the motto upon which I built my career. But the idea was, look, the commodity markets are building microprocessors for PCs. And we're either going to figure out how to do that or we're going to die, right? And so we did. And Don, he brought in Don, who wrote the first ever Ethernet drivers for Linux. And that turned out to have a little bit of an impact if you think of the modern data center world and how many billion machines over the last 30 years have run Linux, and just assume that the network would work, because Linux was you could talk over a modem, but not over a network before that. So we're a long way from those days. But I remember it was for the 3Com 3C509 network card, and you could finally put it in a PC and work, and we could network commodity PCs together and start doing message passing. 2 years after that, we had the MPI standard for the first time, right? And about 6 years after that, you started MBAPICH. So when we had different kinds of RDMA-based networks to run this over instead of just plain Ethernet. because by the way, those 30 companies had 30 different, all purely commercial, closed source message passing libraries that used totally different semantics and didn't talk until Express and then PVM. So we need to do this again, right? So the gist then was silicon's expensive, we're going to use commodity parts, right? So figure out how to put networking in Linux, use commodity processors, and the entire top 500 had changed within 10 years, right? Every big machine in the world was essentially a commodity cluster. And if you think about it, where did GPUs and computing start, right? I mean, the G still stands for graphics, technically, right? And graphics processors, they were built, you know, back to the 80s and before. When NVIDIA was getting started, it was to do graphics and to do gaming. And it wasn't until about 2004 where, you know, when Ian Buck wrote CUDA, along with a couple of others, to start thinking about what if we use these GPUs to do something other than graphics, right? They have these big streaming memory things. They're essentially sort of vectorish-like units. We could do general purpose computing on them. And that took many years to catch on. And then they got really lucky and the AI frameworks got written on it. But that was about writing these gaming markets to get cheaper processing to bring into scientific computing. And that was also sort of out of the academic community, right? So universities led on this. The agencies followed kicking and screaming, right? DOE still makes NRE investments with vendors, thinking they can change the silicon they build. But making a few $100 million in NRE investments isn't going to change a $300 billion market. So we can do this again, right? And this is what we need to do again, is use AI hardware for science, right? You can find 100 reports in any country about AI for science and science of AI. What we need is AI hardware for science, right? It's the next Beowulf project, right? What if we built a cluster? Because once Beowulf started, for every chip that came out, there was a joke that ran on Slashdot for about 25 years. Might still be going. What if we built a cluster of these? So what if we built a cluster of AI chips, right? For our next gen of scientific computing? What's that going to mean for us, and what are we going to have to do about it? So hold that thought in your mind of building a cluster about it, because it's actually very closely related to the last thing I want to talk about, which is sustainability and the sort of notion of green computing. There was a conversation yesterday afternoon at EDUCAUSE about this, but among CIOs, but green computing has largely been considered a data center problem, right? Can I get better cooling technologies? Can I make my machines greener somehow by making my data center better, right? And there is stuff we can do in the data center. And although those things are all good and important investments to make, and we're making them, I would argue it's not where almost all of green computing is going to happen, right? So, you know, most of what we've been doing in cooling, which is where we talk about this, is can we make the cooling more efficient? Can we make the cooling more efficient? It's had very little to do with improving power use efficiency or overall sustainability, right? It's really about making stuff work, right? As I mentioned, we're going to be at, apparently I didn't save the last version of the slides, but we're going to be at 216 kilowatts a rack next year. We've been running 70 kilowatt racks for 3 years. We've been running 60 kilowatt racks for 5 years. The only way to do that is liquid cooling, right? So we didn't do liquid cooling because it's more efficient than air cooling. It does happen to be more efficient than air cooling. But we did it because everything would explode otherwise, right? And catch fire 20 minutes after we turned it on. And the efficiency was just a happy side effect, right, of this. And I took out the picture of the server. The Grace Hopper servers we have a heat sink that's about this big, weighs 16 pounds, right, to run one of those in air. The metal for that is probably more expensive than the GPU, although GPUs are more per ounce than gold right now, if you actually look, and gold's up. So we've done cooling technology so that we can make things efficient. And, you know, our cooling has gotten better and better, right? You know, if you go back through the years, we had, you know, it was underfloor air at the edge of the room through crack units, comes up through floor tiles, and then gets sucked in through the ceiling again. We started changing that for us. It was 2008 where we couldn't do that anymore. With Ranger, we did in-row chillers, enclosed hot aisles, started sucking things up. Again, turned out to be more efficient. By Frontera, we were into direct liquid cooling, right? Piping stuff across processors. I know they do that here now too at OSC. With CoolIT, CoolTera, Vertiv, whoever you're using, Motivair, there's a whole bunch of players in that now. with Frontera and Lone Star 6 down there, that looks like a big coffin. Those are the immersion tanks where we're just dropping them under mineral oil, right, and running them fully immersed to get density up. We've added chilled water storage during that period in 2012 so we can offload the power grid at peak demand. I guarantee you it's over 100 in Texas today just because it's August, so I'm therefore right. It's 107 when I landed in Dallas on Monday. But so anything we can do to offload the power grid at peak demand is worth doing. We have some direct solar. We've bought wind credits. We're doing 100% wind credits in the new data center, although wind credits and all wind are two different things. But we're raising the water temperature to 86 degrees in the next ones. We don't have to chill nearly as much water for the new data center. And all of that is great for efficiency. And it'll probably keep getting better, right? We're looking at heat spreaders, so we can do 2,000 watt sockets in immersion. By the way, the forecast power for the Grace Blackwell board, the unit, for one Grace dual Blackwell module is 2,700 watts. Right? So you put two of them in a 1U shelf, that's a 6,000 watt node, right? So 6,000 watts per that much of your rack. So the average IT data center has a 6 kilowatt rack right now. And now it's that much space. So there's definitely new innovations out there, right? ZutaCore using multi-phase cooling, Childyne with negative pressure, direct liquid cooling. These improve density, we reduce leaks, we're going to use warm water, so we have to chill less water, particularly in non-Texas climates. And PUE will get better, but we're getting diminishing returns on this. And it's for the same reason you do in software, right? It's Amdahl's law for cooling, which is, in 2018, data centers were maybe running at a 1.7 PUE. In 2000, they were running at about a 2, right? So for every watt you were using in computing, you'd use a watt in cooling. And that's pretty inefficient, right? Now I would say most everything, you can't find one worse than 1.5, but everything new build is 1.2 or better, right? We've been at 1.2 for a while. Will probably be like 1.15 in the new space, right? So when you got from 2 to 1.2, we reduced all data center power by 40%, and that's awesome, right? But getting from 1.2 to like perfect is going to get us 10 or 15%, right? Because you have smaller and smaller fraction left to optimize, and that's a huge issue, right? So, and we're not going to get theoretically perfect, and is there really a big difference between 1.1 and 1.107, right? That's not going to have a significant footprint in how much power we use in the data center. So we can keep investing in this stuff, but we have hundreds of gigawatts of data center being built. I think 75 gigawatts of AI data centers are going online this year, which is roughly the power consumption of Texas in the summer. 30 million people. So thousands of terawatt hours per year, 2 or 3% isn't going to make a huge difference, right? In that, so. And if you're, PUE is 1.x, at any value of x, you still have the 1 to deal with, right? Even if we make x 0, right? And the 1 is now the dominant factor. So, so if we want to do sustainability, we have to do something other than fix the data centers because there's just nothing left, right? In terms of data center optimization. There's a little left, but it's not it. So, so if you're going to make sustainability of a problem, your problem, and there's arguments to say, look, data centers aren't really actually the problem compared to, say, transportation. And if we can do things in data centers to figure out carbon capture and better storage and better transportation and a green power grid, then data centers wouldn't be a problem. But nothing we're going to do in the short term and nothing you can do is going to unilaterally change how the entire power grid works in the world, right? So, but there is stuff we can do, right? So, and again, we keep trying to improve efficiency. We're going to 100% renewable. We've added a hydrogen fuel cell in the current data center. We're looking at storage technologies so we can use more real renewable instead of just credits. We're thinking a lot about power management, right? So we're building out actually a smaller data center than we would have because with the Grace Blackwells, Grace Hoppers now, right? You have a CPU, 2 GPUs on a single module, and you can limit the power to the module. So I don't have to build out data center infrastructure for the max power of all 3 chips. I can just say, I'm going to set that module to consume 2,000 watts, and I'm going to put it between those chips in a way to optimize performance and never let all 3 of them run at max power because it turns out no real code will do that anyway. In fact, the current Hoppers are 900 watts, and we can't find a user code that pushes them past 650. So why am I building out all these big transformers if we know that instead of just doing smarter power management? So again, we're going from 10x the max double precision performance of the 6 megawatt Frontera system and a 9 megawatt system, right? So power up 50%, performance up 1,000%. And again, incorporating renewables helps, but there's limits, and I'm running out of time. So if we really want to get serious about efficiency, we need to build better software. And this is where you come in, right? Better hardware would help too, but again, hundreds of billions of dollars in AI market's going to drive the direction of hardware, and there's nothing we can do about that. What we can do is run codes better and write better software. So, and there's plenty of information about this, right? So we know, for instance, that your peak flops per watt gets 5 or 6 times better if you move to GPUs, right? But outside of AI, we have a lot of codes that can't do that well. And you can make an argument about you get the same percentage of peak flops out of a CPU code or a GPU code, but getting 5x is a lot better than getting 15%, improving your cooling, right? And we know, and we don't really talk about, that most codes run at a single-digit percentage of peak. For some codes, 1% would be a serious improvement over where they run, but for most, it's 8 or 9. There's a few good chemistry codes will get in the 40s of peak, but nothing gets above about 45, except LinPack. But the problem here is, of course, software's hard, it's diverse, it's beyond our reach, it takes people. But a crappy job on software where you could potentially get 1,000% better is better than a great job on data center where you can only get 10% better, right? So we know it's possible, right? So this is just gigaflops per watt. I've shown this before, right? The reason Frontier is in MI250Xs from AMD is that's an 85 gigaflops per watt part, whereas your standard CPUs are about 10 gigaflops per watt. And we know that architectural choices are the same, right? They're both out of the same, TSMC 7 nanometer process for your Milans and your A100s. And part of that is they made the circuits simpler in GPUs, which means they push more of the onus on getting performance back to the software writers, you guys, right? No more complex branch prediction, the fetch decode, execute cycles that are so expensive in power. And again, there's nothing you can do in hardware that's not related to software one way or another. So that was just some analysis of in the OS where all the power goes. But what we're seeing with the new AI accelerators is even simpler. Just do tensor ops. Don't really do anything else, right? Just do them at low precision. So that's making more efficient chips if we can write the software to use them. So, and it gives us opportunities. So I mentioned earlier that, if you look at, say, FP64 performance, right, for vectors, 34 teraflops, this is H100, I think. Tensor core, matrix operations instead of vector, 67. FP32, about double FP64, what we've always had through all the years. If you do 32-bit, you get twice as good as 64-bit. Look at the TF32. It goes from 67 to 989, right? There's a factor of 15 in there versus your double precision tensor core, right? So, and they've maybe relaxed some constraints in the IEEE standard, which is why it's called TF32 and not FP32, different number of bits in the mantissa. But by doing these sort of little 4x4 matrix ops, they're getting huge performance improvements, and those are the same number of watts, right? However you run the chip, right? And then it keeps on going as they go lower. But maybe we need to figure out how to use these mixed precision matrix ops, given that they're 30 times faster than our double precision vector flops. So, and that can be hard, but there are things that are easier, right, without radical changes, right? For instance, you can change the balance in CPUs by improving memory bandwidth. And I realize I'm over time here, DK, so I'll finish up, right? But so typically on the Sapphire Rapids, if we just put in HBM instead of DIMMs, we're getting about a 70% improvement. And the part with DIMMs is 350 watts, and the part with HBM is 350 watts, right? So watts and flops aren't the limiting of our code performance, right? It's the balance of the architecture, right? So with HBM, right, same peak flops, same power per socket, but I've almost doubled my performance, right? Again, much more valuable than making a cooling improvement in your data center. And there's many other configurations are possible. One of them is, using ARM. So I promised benchmarks I'm going to do these really fast, but we took about 20 applications, and when we were going to move to ARM, it's like, can we actually do this? So I built these out on Vista, with the Grace CPUs, on Stampede 3 with the Sapphire Rapids CPUs, and the AMD is getting screwed because I'm using Lone Star, which is slightly older, and it has Milans. And then on these charts I'm going to show, they're all in speed up. So 1 is a Frontera node, our baseline system. So that's an Intel Cascade Lake Platinum 8280 Xeon. And so if I take a pretty wide range of real apps, 9 apps here, weather, chemistry, seismic, molecular dynamics, direct numerical simulation, lattice quantum. And I compare, and I'm also, so terrible at colors, I'm an engineer, but I was worse than normal. Intel's in green, NVIDIA's in blue, and AMD's in the middle in orange. So if you look at these, this is raw performance per node, right? So for a single node benchmark, 2 sockets of Sapphire Rapids, 2 sockets of Grace, 2 sockets of Milan. And you see, while there's different winners on different codes, for the most part, the Sapphire Rapids with HBM, top performing part. Those nodes are running at 1168 watts typically to run these benchmarks. So the Grace nodes run at about 500. So if I take that same thing and I divide by the watts per node, the first gen ARM out of NVIDIA already is outperforming all my other sockets. So raw performance, Sapphire Rapids Xeon is my winner. You want the fastest single socket environment be damned, Stampede 3. If you want the most power efficient CPU to do it, use the Graces, right? The ARMs, right? 8 out of 9, it's the winner. And sometimes by substantial margins, except for eFings code. We'll have to figure that out. He'll tell you about that at 11, since he's here. And also for software, let me just say that it's not just, okay, you downloaded a code, it's 1 million lines long, it's in Fortran, you don't want to change it. This is a measure from a paper I found not too long ago on green algorithms, where they came up with a metric for carbon footprint of your code. And almost every code, this is runtime versus cores, right? Thanks, Watch, for helping out. And you see that knee, right, where the first derivative changes in your improvement. In this code, it's like 15 cores. And it keeps getting better out to 60 cores. But you're adding power more or less linearly, right, when you run on those cores, and you're not getting performance return. So runtime is the green graph. The orangish one there is that carbon measure. And it says, just run on 16 cores and don't use the other ones. And you get a much better carbon footprint, even though you're getting a little bit slower runtime. Right, so everybody can pick the right number of cores, even if you can't recode to use mixed precision algorithms, right? And if you can recode to use mixed precision algorithms, it can work really well. Some numbers from David Keyes. So we need to incentivize that. But if we really want to do good AI hardware for science, and we want to do good AI hardware for sustainability, exploiting this sort of mixed precision is going to be super important. And even if we only get a 10% improvement in software, it's more than we're going to get out of cooling. So let me stop there and say thank you. And I'm sorry I talked for so long. So, yeah.
We have time for a few questions. Any questions? Yes.
Yeah.
So in terms
Yes,
of,
I want a nuclear reactor. That's where you're going.
we'd love to have a nuclear reactor.
Yes.
So in terms of sustainability, what role do you see like a microgrid playing? We talked about grid, and we're not going to get anything better out of the grid. But in terms of microgrid, do you see any role for microgrid in improving sustainability, ostensibly for the data center, where there's not a lot of improvement that can be done, but maybe there's something there?
Sure. And yeah, and I heard your talk about this at PERC, and I asked you, can we do it on the main grid? That talk. So that was your talk, right? Didn't you? Yeah, on the small modular reactors. Yeah. So not to mention yesterday, but I do think there's a role, right? Because as we incorporate, I mean, so we built a mini grid in our data center, and we started doing, we had a machine in 2015 that we ran right off 380 volt DC. So we built out a whole 380 volt DC grid so we could pick power directly off the solar panels and without hitting any transformers, run it right into the racks, right? So we had to, and we needed a grid input when it was dark. So we had to build out a mini grid, right? To sort of balance when we had renewable power, or, a steady state small modular reactor would be the same thing, right? It's probably producing some of the power, but not necessarily all, and you need to store it somewhere, either back to the grid or in local storage. So I think, yeah, for operational optimization, there is a role for that stuff, particularly as we have to incorporate storage, renewables, things like small modular reactors, fuel cells, any of that kind of stuff, where the sources of generation aren't going to match the consumption pattern on the machine. And we have to balance that out. I think microgrids are a big part of the solution there. Mm-hmm.
Any other questions? Can I have one more? Yes. Hey.
Importance, so not only in terms of the, getting the more performance or the raising the utilization, but also for the sustainability there. But, when I talk with some of the software folks, then they really want to run the old as is with the different parameters, regardless of how much time it's going to take or how much power it consumes. They just simply, it seems like they simply don't care. So my question is that, do you have some plan or idea on how to motivate those software or the application folks to move on, to more optimize their code for better sustainability?
Yep. So if you're online, the question was about the general conservatism in science around running the old code at any cost and not necessarily improving it. And I think one of the problems there is nobody has incentives to make it better, right? You don't charge your users directly for the cycles that they burn on that code. The cloud guys aren't incentivized because they sell computing by the hour, right? So the more hours you take, the more money they make, right? So why would they want you to have a more efficient runtime? But we do nothing to incentivize this for users. And in fact, we don't even make available that it necessarily could be better, right? And there's legitimate concerns about, the old joke of when somebody gives a talk with experimental results, everybody in the room believes it except the person giving the talk. And when somebody gives a talk with computational results, simulation results, no one in the room believes it except the person giving the talk. Because you have to do the validation and verification work, to move codes forward. So how do we incentivize that? One, I think we have to start giving people information about how efficient or inefficient they are. So sometime in the next year, we're going to start reporting total joules on every job that runs, and maybe with some comparables, right, as to what could be run, so that the people get some idea of, is your code efficient or not, and how much more efficient could it be? But, what if we went to energy-based charging, right? It's not something we're going to do in the short term. But if instead of saying, this costs you 1,000 CPU hours, it's like your budget is this many joules. And when you run out, you don't get to use the machine anymore. Right? And we could, that would be complicated for a number of reasons, because the most efficient thing would be to run on one core and leave all the others idle all the time, which is not how we want to use the machines. But we're going to have to create incentives. And I think tying it to sustainability, right? The problem we all have is we can't get the agencies to pay for software, right? Right? They want to fund machines sometimes, right? They'll fund experimental work, but nobody wants to pay for code maintenance or performance improvements in codes, right? Anywhere in the world, no matter which government or agency you have. But if we started saying, look, this is the key to lowering the power bill, this is the key to, green outcomes, and we can demonstrate results on that, this may be the backdoor way to get people to pay for better software. It's using climate as the motivation, and then it's a win-win, right? Because one, we get money for software, which we all desperately need, and two, we actually address this sort of green computing problem. So, but I think, yeah, we have no incentives, and we need to create incentives, and I think, there's the, using AI hardware part is to make scientific computing better, but if we can tie it to green outcomes, we have a fair chance of getting funded for it. So it's a long shot, but, got to try something hard once in a while. So yes, incentives and information, I think, is really the answer, I hope.
Okay, thanks.
So let's proceed. We can have more, I think Dan will be here throughout today. So we'll have more interactions later on. We'll proceed with the schedule. So let's give a big hand